This video is all about the scientific method. As you're thinking about how to structure your science fair projects, this is something you really want to think about. So the first thing is you need an idea. Let's say my idea is I'm going to test the water in my local stream. So I start to ask myself, what am I going to test it for? How am I going to test it? What do I think I'm going to find? That's when I do preliminary research. I can do my preliminary research a couple different ways. I can use my computer. If you're using your computer, I would stick with the databases. Do not do a general Google search. That's probably not going to help you. Though you could look at Google Scholar. That would be a better place than just plain old Googling the whatever it is you're trying to look for. Or you could actually go to the library, look at books and journals in the library, ask the librarians. All of these are places to do preliminary research. From that preliminary research, you narrow down your idea so that you can make a hypothesis. Maybe I make a hypothesis that there are elevated amounts of lead and arsenic in the local stream. Okay, that's a hypothesis. But remember, I have to have a reason to make the hypothesis. My preliminary research must have said, for example, that at one point upstream from where I'm going to take the samples, there was a factory that worked with lead and arsenic, and they might have contaminated the river. I have to have some reason for saying that hypothesis. A couple other things to remember about hypothesis. Notice that is a testable statement. Okay, it's not so vague that it can't be tested, and it's not something that's known in advance. I don't know yet if there are levels, higher elevated amounts of lead and arsenic in that stream. I'm postulating it. I'm hypothesizing it based on my preliminary research. Now, from there, knowing what it is you want to study, you can go and design experiments. Couple things to remember about experiments. One is that the experiments can only change one variable at a time. So even though my hypothesis said lead and arsenic, I need a set of experiments that are going to test for lead, a set of experiments that are going to test for arsenic. I also need a control. For example, if I have some method of testing for arsenic, then I get distilled water. I test the distilled water for arsenic, and then I have a baseline. I know how the arsenic test works, and I can say, see, look, this is water that does not have any arsenic in it, and you can use that to compare to the stream water. Everything's carefully controlled. Now the experiment gives me results. I've listed the results here in a table, which is always a good way to do results. When you are talking about your science fair board, tables should give way to graphs. On your science fair board, pictures are the way to go. But whatever method you choose, very organized, so somebody can look at it at a glance and know your results. Then what happens is you draw conclusions. My conclusion might be the amount of arsenic is within acceptable limits, the amount of lead is too high by 2.1%. Something along those lines. That's a conclusion. Then you can say, well, let me look back at the hypothesis. What you cannot say is the hypothesis is proven. Nothing is ever proved in science. What you can say is the hypothesis is supported or it's not supported. And it's all right if your hypothesis is not supported. That's fine. It will also be very true that when you are doing the experiments and you have the results, you often have to go back change your hypothesis, run some more experiments, get some more results. This is all a very circular process. Eventually, of course, a scientist will communicate their results. You will be communicating your results through a science fair board and through an oral presentation in class. A scientist would go to conferences, will publish papers where other scientists that will then read it and check and make sure their results are reproducible. Science is no good unless it is reproducible. So this communication part is very, very important. Now your book goes on after that and talks about theory. A theory is not a hypothesis. We tend to use in English those two words interchangeably, but it's not true. There are very few theories in science. Atomic theory, for example, is a theory. What a scientist means by theory is not a guess, not a hypothesis, but something that has a lot of evidence to back it up. Years and years of experiments that all reach the same conclusion is behind a theory. Theories can be modified. New experimentation might lead to the modification of a theory. But generally, theories are very well accepted by the scientific community. By the time it's a theory, pretty much every scientist agrees this is the way to go. The problem is, in science, it's very difficult to prove things. So a theory is not proven, but it's as close as you can get in science. It's got a lot of evidence to back it up.